Hello. Just as a little introduction, so my name is Maxime. I'm from Belgium at the Free University of Brussels, and I'm at the moment a PhD student still. And I'm mainly working on moving object databases, more specifically MobilityDB, which is a Postgres extension, a spatio-temporal Postgres extension. Essentially, it's a temporal extension to PostgIS, which most of you probably know, which is itself a spatial extension to Postgres. And so in MobilityDB, we work with moving objects, so temporal points, as well as other temporal data. And so we have different new types to store this type of data, as well as indexes that are able to work on these types, and a bunch of functions and some optimizations. And while working on this, we realized that the indices, so GiST and MSP-GiST indices that we use for our data type are not very efficient just because of the way the data type is implemented and is being used. And so this led to the current work that I'll be presenting. But this work is not specific to our data types. It's actually a bit more general. So that's why I'm presenting it here, because it can be used for a bunch of other data types related to PostgreSQL. Before starting to talk on this topic, let me give a brief overview of the existing index capabilities of Postgres. So the most important one that all of you know is the B tree, which is used for mainly one-dimensional type of data. So data that can be sorted in one global order, like integers, characters, dates, and so on. But then we have multi-dimensional data that cannot be easily indexed in a B tree. So for this, we typically use GiST or MSP-GiST indices. The main use case of this are geometric types. PostgIS makes heavy use of this, but also the range and multi-range types, which I will go into more detail today. Then we also have GIN, which is mainly used for text search, JSON types, and arrays, which essentially, under the hood, uses B tree, but can index multiple entries for a single value. So let's say a document contains a bunch of words. Each of these words are going to be indexed in a B tree, and then can be queried using GIN. And so GIN is related to the B tree, but allows for more types of operations. And then we also have hash and brin, but these are not too related to what I'm going to talk today. And so looking at all of these data types that are native in PostgreSQL, for some of them, the existing indexing techniques are not efficient or not efficient enough in some cases. And in other cases, for example, for the array types, there are some operators that we might want to add, custom operators, that cannot really work with the current indices. And so I'm presenting a new index type, a new multi-entry GiST index, as I call it, which can improve these problems, can fix these problems. So for the moment, I will present all of these solutions for the multi-range type, which is in Postgres. And then later on, I will show our use case that started this whole project in MobilityDB for trajectories. But so starting with multi-range types. So multi-range is quite new. I don't know if we can call it new. It was added in Postgres 14. I think it was 4 years ago. And essentially, one multi-range represents a distinct set of ranges. So you can have ranges with gaps in between. So here you have 4 examples of multi-ranges. And with these multi-ranges, you can apply a set of operators. Typically, you could ask, okay, which are the multi-ranges that contain the number 14, for example? And here, visually, you can see the second multi-range contains number 14. The other ones do not. And you can do the same with comparing the multi-range to another range, or comparing multi-range to other multi-ranges as well. So here you could say, okay, which of the multi-ranges overlap this range 6 to 10? Well, that would be all 4 of them. But which one contains the range? That would be only range number 3, for example. And so this is typically the kind of query that you might want to speed up using an index, right? you're looking for all the ranges, multi-ranges that contain number 14. The result is a single tuple. You might want to skip all of the other ones and using an index scan. So how are these multi-ranges currently indexed in Postgres? So since it's not one-dimensional data, since you have ranges, start and end value in the ranges, it is multi-dimensional. We need the GiST index. So these are indexed in GINS. But you cannot index the multi-ranges as is. So for this, we first merge the multi-ranges in a single global range. So for example, in the first one, we get a range that goes from 0 to all the way to 24. And this is the range that gets indexed in GiST. And then this is used for the index scan. So in this case, let's say we have these 4 ranges in the index. We're looking for all the multi-ranges that contain number 14. Well, the index is going to tell us they all contain it. And then using a recheck, we will filter out the 3 that do not. But this is quite inefficient. So as we see, we have a lot of false positives that the index produces that we do not want, because they will slow down the query. And this is not just a theoretical problem. This happens in real life as well. This is a comment on the thread, Hacker News threads related to the multi-ranges. Someone saying that they had this issue where they were using multi-ranges for scheduling purposes, and the indexing was not working as they wanted. So they used an ad hoc method of unnesting and indexing individual ranges, but this is not ideal, of course. And this problem is actually known for quite a while. So Alexander, who was one of the people working on the patch that implemented the multi-ranges, in this thread on the PG hackers, he mentioned that this indexing was known to be not ideal. And ideally, we would want to split the multi-range into individual indices, individual ranges, and index that. But this is currently not possible. So he says we would need something that's GIN-like, but instead of a B tree, we would need a GiST or an SP-GiST index inside. And so this is exactly the solution that I'm showing today. But so this was already tried before. He mentions the vodka index. I don't know if anyone here was in PGConf 2014. Yeah, so you heard about this before. So this was already attempted, but for whatever reason was a bit abandoned in favor of another type of index that they pursued. And here the idea, they called it vodka, was to modify GIN to replace the B tree with GiST or SP-GiST type tree. And their use case was mainly HStore or JSON-B. But here, of course, I'm presenting this for multi-ranges and as also MobilityDB trajectories. And they went a little bit different approach than what I did. So they started from GIN and modified the B tree into SP-GiST-like tree. And I did the other approach. So I started from GiST and I added GIN-like capabilities, but they are somewhat equivalent techniques. And so here you see this access method, I called it MGiST for multi-entry generalized search trees. And you see how it fits with the other access methods. And of course, this works for GiST, works also for SP-GiST. The idea are essentially the same in both cases, where you add GIN-like capabilities to either GiST or SP-GiST. So how is this MGiST index designed? This is here an extremely simplified view of GiST, but I think the main parts that are different between GiST and MGiST appear here. So you see we have the tree. During indexing, our value, here we have, for example, the multi-range from 2 ranges, gets compressed first into a single range. And this is the entry that gets stored in the tree. And this value is always combined with a tuple ID so that we can know which tuple this refers to. And then during querying, let's say we have a predicate, find me all the multi-ranges that contain the number 10. This, we go through the tree and we find all of the tuple IDs that match this predicate. But then, of course, we need to recheck the predicate on the actual value. And in this case, for example, the index would have returned this tuple because 10 is contained between 0 and 20. But the recheck will say, OK, actually, predicate does not match. And so would just skip this tuple. So now how this changes with respect to MGiST, the idea is that just like in Gin, we want to split our value before inserting it in the index. So here, extract value is the exact same method as Gin has, it's the same name, and simply takes a value and then returns a set of entries that we want to insert in the index. In the case of multi-ranges, essentially we create one entry per range. So here we have two of them because our initial multi-range has 2 ranges. And of course, since these two correspond to the same tuple, they have the same tuple ID. And then during querying, we just do the same thing as we did before. And in this case, the value 10 is not found by any of the 2 tuples. So in this case, tuple ID 1 would not be returned by the index. So this false positive that was returned before is not returned anymore. And so we can actually even skip the recheck in some cases. In this case, we can just skip the recheck. But of course, we have a small issue here, is that if for some queries, some predicates, we might hit 2 of the entries with the same tuple ID. So we need to deduplicate this before returning the tuple or applying the recheck on the tuple. So we have an additional deduplication step, either by simply doing a bitmap scan. So this does deduplication for us, or in index scan, we need to do that manually. And this is, of course, internal, so this is not user-defined, but the extract value is a user-defined method, just like all the other ones that GiST has. And for those who know Gin, they know that extract value is only one part of it. You can also have extract query, which will, instead of splitting the values that you're indexing, you should split the query value and then apply the same techniques and use a try-consistent method to decide, based on the results of this querying, which of the values we need to return. But I will come back to this later on if I have some time. But essentially, what I'm showing here is the result of this. This addition of the extract query is still a work in progress. But you can see that you will see that even with just adding extract value part and the deduplication, we also already get large benefits. So here I'm giving the example of the multi-range. This is just a trivial example with random data, but you will see that we get large benefits. So let's say we have a table, TMR, the multi-range table with multi-ranges. We duplicate it 3 times. In the first case, we have no index on the table. In the second case, we have a GiST index. And in the third case, we have a MGiST index. And these tables, they all have the same, in this case, 10,000 rows of multi-ranges. You can see, of course, since the GiST contains multiple entries per tuple, it's a bit larger. In this case, it's almost 3 times as large. But it will allow us to provide larger speedups. So let's say we are trying a simple query, which is count all the multi-ranges that contain the origin, so the value 0. When we do that on the table without index, we get a simple sequential scan followed by an aggregation. And you see this takes about 1.7 milliseconds. But also what you can see is that most of the rows are filtered out. Actually, our result only contains 7 rows, so the count is going to be 7. And so this is a typical query where we expect an index to provide a large speedup, right? Because we're filtering out essentially all of our data except for the 7 rows. But what we can see is that when we run the same query on the table that contains the GiST index, we don't get any speedup. Actually, it's 2 milliseconds instead of 1.7, so it's slightly slower. And you can see that we still have a lot of recheck that removes rows. So this is a clear sign that our index returns a lot of false positives, and this slows down the query. So now instead of just doing sequential scan, we have to scan the index as well as still doing the recheck and removing all the false positives. So this takes a lot of time. So now what happens if we do the same thing on the table that has an MGiST index on it? Well, you can see that this goes much faster. We have 0.08 milliseconds. And this comes from the fact that the index itself returns only 7 rows. No false positives in this case, and so no recheck necessary. And so this goes, in this case, much faster, about 20 times speed up. Yeah. So this was the first example of a type that can benefit from an MGiST index, in this case, the multi-range type in Postgres. But of course, the MGiST index here is not here to replace GIST, right? In the same way as GIN and B-tree are, the GIN does not replace the B-tree, the MGiST does not replace GIST. It's going to be more efficient than GIST in some cases. In this case, I was showing the example of the contains operator. But in other cases, it might not be efficient to use this new index. Essentially, what you can realize is that MGiST is going to be very beneficial every time your operator, every time your gaps in the multi-ranges matter for the operator. So this is for the overlaps or for the contains. But for example, strictly left, the fact that you're taking the multi-ranges as individual ranges or a single big one, you will not have any difference. So in this case, it's GIST is good enough. So here I mentioned the multi-range type, but I also said this is not the only one that can benefit. And in this previous talk in 2014, they also mentioned this, called it spaghetti indexing. There might be cases where spatial data has the same problem as what we had with the multi-ranges, where the index is not very beneficial. And this also relates to the path type in Postgres, but I'm not going to go into detail on the path type. Instead, I'm going to talk about the trajectories in MobilityDB, which are quite similar. So as a quick refresh or deeper explanation, in MobilityDB, the main data type that we add and that is being used by users is called tgeom point, which is a temporal geometry point, which represents the evolution of a position over time. So it's a moving point, essentially. And so this type of data can be used to store and represent the movement of cars, for example, on road networks, or the movement of ships on the sea. And typically, this data comes in this format. So for this, you might need a PostGIS extension to store the position. But essentially, you would have a big table with different trips that are represented either via some identifier, here the MMSI, which is the identifier of a ship. And then you also have points with their longitude, latitude at a given timestamp. And you have a bunch of rows, and together, if you group them by MMSI, they can represent a trajectory, the movement of a ship, for example. And you can have a lot of these points in the same trajectory. Here, for example, 9,000 rows together form the trajectory of this ship numbered at the start here. And you have this for all of the ships in your data. So here, for example, this would be a huge table with 7.5 million rows. But not 7.5 trajectories, right? And in MobilityDB, this is represented in a different format. This is the format that's being used. So essentially, we group all of the rows of the previous table into a single row in MobilityDB. And so you have a single ID, and then a single tgeom point, moving point, that stores the evolution of this position at timestamp from the start to the end of the trajectory. So this is more compact visually. We have one row for one trajectory, so it's a bit easier to write queries about it. And then MobilityDB also offers a lot of functions that can be applied on this. Let's say we want the speed, the average speed of this ship, and so on. But the problem that we have here, since now a whole trajectory is a single tuple, well, this will cover a big spatial extent. Let's say on the top right, you can see the small white line here might be the trajectory of one vessel over a day, maybe, or a few hours. And then if you want to create a single object to insert into a GIST index, typically this is a bounding box. Well, the bounding box is going to be extremely large, right? And so we have the same issue as we had with the multi-ranges. Since all of these bounding boxes are going to be really large, they will not be efficient in filtering out the tuples. When, for example, we have a query that says, find me all the trajectories that pass through some spatial extent, some small bounding box. So here we see exactly the case. On the left is what is currently possible using GIST, where we have our trajectory in red that's indexed using its bounding box. And then the query value, this small commune in Brussels, gets also queried, or we query the index using its own bounding box. And according to the index, they might overlap, right? The trajectory might go through the commune, so the index will return the tuple, and we need to recheck to, in the end, just throw it away. So instead of doing this, we might do just like in the multi-range case, insert multiple bounding boxes instead of a single one. And so in this case, you could split your trajectory into, here it's 7 bounding boxes. And then when we query the index with this query value, the index does not return this tuple. And so we filter out more false positives. In this case, it's not perfect. So unlike the multi-ranges, we might still have some false positives. But the idea is that by using multiple bounding boxes instead of a single one, we reduce this problem. And so here I have the same thing where I'm running a query that has this condition. So in this case, the query is, find me all of the trips that passed through some query points, might be some points of interest. No, that not passed through, but passed within 10 meters of these points of interest, right? And so you can imagine that this function, ever within, will add an index condition if there is an index present. That is, okay, the index condition is the trip, so the bounding box of the trip has to overlap another bounding box that's formed by taking these points of interest and some area of 10 meters around, right? And here, this is done with the trip being represented as a single bounding box. So we're in the case of GIST index. And this takes about 30 seconds. And you can see here that, okay, this is a nested loop. So these values are only for the last loop of this nested loop. But you can see the actual amount of rows that are matching this condition are 18. And we initially returned almost 1,000 of them. So we see a lot of false positives again that we want to reduce. And so this is the exact same query, but instead of GIST index, we have MGiST. And so the trip has been split into a lot of smaller bounding boxes. And you can see that not only does this take less time, but the amount of rows that are filtered out is reduced from 900 to about 40. So we have way less false positives, and this indeed achieves better execution times, here about 10 times speed up. So this was the second example. So we have multi-ranges on one side, trajectories on the other side. Here actually I wasn't really going into too much detail, but these trajectories are 3-dimensional, so x, y, and time as well. But of course, if you're working with, let's say, just PostgreSQL line strings, 2 dimensions, the idea is exactly the same, right? And initially, I was mentioning some other problems that could benefit from this indexing. And so I have two more examples that I won't go into detail, but just explain the idea of how this could benefit. On the left, let's say we have a PostgreSQL geometry collection. So here it would be a multi-polygon. Instead of storing this multi-polygon as or indexing this multi-polygon as a single huge box, you would create one box per polygon. And this might also improve some operations that you do that use the index. So this is one case of the multi-polygons, but you can imagine collections of other data types. Let's say a point, multi-point might be the same idea. And on the right is another idea where imagine you have a single polygon, but it's very large, and by large I mean it's created with a lot of small edges. So this could be a few thousand edges to create the outline of our polygon. A point in polygon query says, given a point, am I inside or outside this polygon? Typically, in the same way, if this is a PostgreSQL polygon, the index will store a single bounding box. And then if you're somewhere inside, the bounding box will say, OK, you might be in the polygon. Then you go to that tuple and you recheck. And the recheck is expensive because you have a lot of vertices of this polygon. So this geometric operation is quite expensive, takes a lot of time. But now if instead of indexing this polygon with a single box, you're indexing with this set of more boxes, not sure how many exactly, you can add to the boxes some metadata. Here we have blue and red boxes, as you can see. You can say, for example, the blue boxes are the ones that are contained in the polygon. And the red boxes are the ones that are on the edge. And so when querying the index that stores these polygons, these bounding boxes, these rectangles, if your point of the point in polygon query falls in a blue one, you can say, I know I'm inside a polygon. I don't need to recheck. And you can reduce this recheck, this expensive part, quite a bit. So this is just a second idea. These are two ideas, but of course, you can imagine that depending on the data type that you work with, you might have different ways of using the index to speed up some of the operations. OK, so this was all using, yes?
So do you have operators in the operator class to do that red versus blue distinction?
So this is not implemented. This is, at the moment, just an idea. But as long as you know how to split your polygon into a set of blue and red ones, so you have to be able to implement this extract value method, then this is doable, yeah. But of course, now the question becomes, how do you split your polygons into a set of blue and red ones? So this.
I was thinking more in terms of how does the index store the fact that it's either blue versus red, so that when you get something back, you know which color it was.
Well, you can essentially choose what type of value, what type of object you store in the index. Currently, it's a single bounding box, but it could be just a pair of bounding box plus Boolean value, and then your consistent function receives this value, which is polygon plus Boolean value, and the user-defined consistent function says recheck or not. And this recheck or not can depend on, was it blue, was it red? So as I said, all of these previous results were using only the extract value, but you can imagine that just like in Gin, you might want this extract query as well. So here I have some time, so I will detail this as well. So this is still work in progress, but I have some preliminary results that show that it can be useful. So let's say we're working with, in this case, the Postgres path type. But as you can imagine, this works for Postgres line string, for MobilityDB trajectories as well. So we have a bunch of paths that mostly overlap each other. And we want to find, so we have a bunch of paths in one table. But then we have another table, the query table, which also contains paths. So now we're trying to find the overlap between two paths and not between one path and a single small query box, right? So the idea is, well, first you index the paths in your value table using MGiST. But then during querying, you might want to also split these query paths instead of querying the index with the bounding box of the whole path. And so when testing this, you can split these values, so the paths that you index in your MGiST index, you can split them into some variable amount of bounding boxes. And you can also split the query value into a variable amount of bounding boxes. And then varying these two, you can see which are most efficient. And so in this case, so remember this was the query. For all of our query paths, count the amount of value paths that overlap with it. If we just do a sequential scan for this takes about 2 minutes. And if we use a traditional GIST index, you don't get any speed up. This takes also about 2 minutes. But then if you only split the paths in your index, but you query it with a single bounding box again, similarly, you don't get that much speed up, just because this query box is then going to be very large. And so splitting the values is in the end not really helpful. But if you split both of them, then you get some speed up. And visually this looks like this. So we have the line at the top, which is sequential scan or GIST. Then you get some speed up depending on if you split only the values. But then if you split both of them, the values and the query, then you get a huge speed up twice. And so you see that this can indeed be beneficial. But as I said, this is the only experiments I have on this at the moment. So yeah, I think I went a bit fast, but I'm getting to the end already. So this is all implemented as a Postgres extension. So as you know, with the extensions, we can do a lot. And the index access methods, we can also add new ones. So MGiST and MSP-GiST are two extensions based on GIST and SP-GiST. And then the MGiST MobilityDB and SP-GiST MobilityDB are two additional extensions that implement our R tree for the new MobilityDB data types. So all of this is available on GitHub. And if you're interested, you can try it out or even contribute if you want to do this. Yes?
Have you heard of the RUM index?
Yes, I have.
Because that sounds a lot like this, but based on GIN.
Yes, well, from what I know, RUM is still using a B tree, right? It's still...
No, it's based on GIN, but adds extra values to it. It could have added the timestamp for a point, or the blue and red for the boxes and things like that.
It's for text search. It's relevant sorting index. It solves a different type of problem.
Okay.
Yeah, from I think it's indeed you can add metadata.
Yeah.
So like the position of this word in your sentence, let's say, but it's still indexing the values in a B tree. So it still has the same issue as what GIN has. You can indeed add some more information, but it's not solving the whole case for these data types. Yes?
I have a question. It's not very clear to me if this is like a set of op classes for the existing like GIST, or if it's like something that is essentially parallel to GIST, right?
It is parallel. So it's a different access method. Okay. And then you can create operator classes for this new access method as well. Yes. So here, the MGiST extension creates this new access method, as well as the operator class for the Postgres path type.
Right. So essentially, I will have like B-tree, GIST, MGiST. Yeah.
How do you decide how much to subdivide the items that are being indexed?
This is a good question, and it depends on the situation that you have on your data type as well. I assume, for example, for the multi-ranges, the solution I gave was one range per, range in your multi-range, right? But if your multi-ranges have thousands of ranges, maybe it's also not that efficient to have thousands of entries. But you want to group some of them into a bit bigger range, but still, let's say your 1,000 ranges in your multi-range would get compressed into 5 or 10 ranges, and you still keep some of the important gaps. So it is a good question, and there's no one answer. It's a bit of a trade-off between the size of your index and the amount of false positives that you will have when querying it.
So are there parameters to when you create the index, or are there?
So, for example, what I did in the MobilityDB one, you can specify a parameter. So there are different techniques of splitting a trajectory into boxes. The one that I showed before was you specify a parameter which says, I'm gonna group this amount of small segments into a single bounding box. And so in the case that was about 50, so if you have a trajectory of 5,000 small segments after each other, you will create 100 bounding boxes, right? 50 each. So that's one option, and then you can specify how many segments per bounding box, and this will change the size of your index, but also the boxes that you create. Yeah. Yes.
So you have this extension, but what would be the cost of teaching regular GiST to handle multi-inserts? Like your operator class, when you're doing compression, is telling that, well, it seems like it's uncompressible geometry, and I want to split it into multiple tuples. And then, like regular GiST could, in a scan, answer that looks like I need the duplication. Is it costly, or what's the reason for going to full extension and not trying the patching core?
Well, you could add that indeed in the core. I think it.
You would.
No, yeah, of course. I think
It's up to you. It's like,
For volunteering.
no. I think that the reason why I went this way is because it's probably easier to present and to offer this as an extension than to tell people, okay, try it on my fork, or offer this. So it's going to be quite difficult to add this as a patch, I believe, at the moment. So I started with this.
Proves the concept that it's fine.
Yes.
It makes sense, and it's useful for temporal data and for geographical data, and maybe consider what would be the cost of having it in core. Right?
so I have a question. Essentially, if I understand correctly, right, when building the index, you expand one value, for example, a path into multiple smaller like steps. But isn't the problem really that when we are calculating the bounding box for like multiple entries, that we are essentially calculating one huge bounding box? And wouldn't it be possible instead to like calculate in the regular GiST like a much more detailed collection of bounding boxes, for example, right? Like instead of like having multiple, the MGiST, which deals with the problem by having like much more detailed like items in the leaf pages, having like more detailed, the combinations of like.
So what you're suggesting is having a single entry, but the value stored in that entry would be more detailed than a single box. Is that? So it's another option, but it's a bit more complex than that, because if you then have this single entry that, for example, stores a list of boxes, then when you index that and you want to group multiple in leaf pages, then you need to be able to create, for example, a union of all children, and that's much more complex if the children are collections of boxes.
Yeah, I mean, like it would need to be essentially at some point, as you go up in the tree, in the index, you would need to progressively like compress those, right? So that is definitely true.
After union, your key must be smaller to represent internal tuple. If internal tuple is not smaller than in bytes,
Yes.
than leaf tuples, then the tree will be infinite. We need.
No, I do understand that you need to kind of like combine those, but you can do that progressively as you go up the tree, right?
And at some point, you will happen to have this compression which replaces object with bounding box, and you encounter the same problem that you need two bounding box for some set of geometries. It's just a matter of at which level of tree we'll encounter the problem, but the problem will persist.
So I've been thinking of, with the, like you mentioned Gin index briefly, and the kind of, and the fact that Gin is kind of this thing, but for B trees. So I've actually wanted for a long time to get rid of our Gin index and just replace it with like some kind of abstraction over the B trees, where you could have a like operator class that can extract values that you then put in a B tree, and then when you search, you kind of put it back together again. Have you thought about, like, it kind of goes back to what Andrea was also saying, like how we thought about actually getting this into core so that there would be, it wouldn't be a separate index type, but just some kind of thing? Or
Yes, yes. Of course, this ideally is the goal. It's not far enough yet so that it's possible. But indeed, as you say, here, if you replace the B tree with a GiST index, well, you can simulate B tree using GiST, right? So you could indeed completely remove Gin in theory and just use this, but then simulate.
Probably makes sense to use this, but you would want to replace Gin with the thing over the regular B tree in Postgres that kind of extracts your keys and then puts them in a regular B tree. Just that you will have multiple entries in the B tree for each row. Like if you're indexing arrays, for example, you would just have, you know, every element of the array in the regular B tree. So like that's kind of what I'm thinking with this. It would be useful if you could abstract this into some kind of an operator class over an operator class kind of thing.
Possible. Yes?
I didn't see an example of a timestamp range or as an operator, because I could see the same situation where you would want to have, like, you know, you were at this location from here, from this range of time, like I lived here. So it's the same thing, just the opposite of, have you thought about having an operator for timestamps or no?
Do you mean specific timestamps of range?
Range of timestamps.
Well, if you're still working with only ranges of timestamps without any gaps, then you are in the same case as a regular range in Postgres.
Yeah, but no, I also have I have a point also.
Yes. Well, it's still a single object. You don't have any.
You might have gaps though too, I can imagine.
Yes, of course. If you have gaps, you can have multi-range, temporal multi-range, and maybe an additional dimension to represent position that corresponds to that. No, yes, indeed, it's definitely actually in MobilityDB, these temporal geometry points. The example I showed is a single sequence from start to end. You're moving, but you can also have gaps in there. And if your position doesn't change, but you only have the timestamp, then it's indeed the case that you're mentioning. So this is another use case where this might be interesting. But the question always comes back to, do you have the problem of a lot of false positives? And this comes from either the gaps, or in the case of spatial objects, you have a lot of area that's covered by your bounding box that is not actually in your object. So indeed, it depends on the data type that you're working with. Yeah. Yes?
Is MGiST based on GiST or clone of with modification?
Yes, so as I said, I started from the GiST code and then added the extract value part and started adding also the extract query that are based on Gin. So but initially it's
GiST. If GiST evolves, do you need to like refresh and add those things?
At the moment, yes.
Okay.
Yeah. Yes?
Often in using GiST, you want a multi-column index with like a boring type, like an integer combined with something like a range. And so we have B-tree GiST because core doesn't come with all of the op classes for those things. So I'm curious, does MGiST come with op classes for all of the simple types?
Currently not, but it is indeed a possibility to add them. If you have, for example, here, you want to split your trajectory into multiple boxes, but you also want to store, let's say, the amount or the size of your vehicle or something like this, you could group them and duplicate this value, put it with each of the entries, and index that. So it is indeed possible, but at the moment it's not implemented yet. Yeah. But then an additional, more interesting question becomes, what if you want to index, you have a column that's temporal point, a moving point, and a second column that's the temporal float value, which corresponds to the speed of your moving point over time. So maybe you want to index both of these columns at the same time so that you can say, okay, give me all the cars that were above 30 kilometers an hour inside this spatial region, right? But then it's a bit more complex because you can split the temporal point, but you can also split the temporal float. How do you combine these different parts together? This is a work in progress. Yeah. Thank you very much. Thanks for your attention.